Chapter 6, Reading the Landscape. Oh, Dan, can you see that big green tree where the water's running free and it's waiting there for you and me with water, clear, cool water? Song, Cool Water by Bob Nolan. Reading the landscape is an exercise in deductive reasoning, one in which facts are collected, observations made, inferences discussed, and hypotheses formed, tested, rejected, accepted, or revised. Prior knowledge and experience are helpful, but not essential. A cautious, deliberate observer can learn to read the landscape and comprehend its messages. Reading the landscape is more like reading hieroglyphics scratched on a stone tablet than reading a book. The surface of the tablet can be rough and worn, the record incomplete or obscured by vegetation. Even so, with practice, messages from the landscape can be gleaned, interpreted, and understood by the careful observer. Reading the landscape is both art and science. Science provides the facts. Art interprets their meaning. A landscape artist sees form, pattern, texture, and tone, and then relates these to each other to form a harmonious composition. To a landscape artist, beauty is its own reason for being, something to be captured on canvas and enjoyed forever. A scientist may view the same landscape and see not beauty, but function, and ask why, storing the answer away for future reference. Why is the land formed as it is? Why is the texture coarse or smooth? Why is the tone light or dark? Why is this pattern here and that one there? Why does a particular kind of tree grow here, but not there? Why is the stream bank eroding? Why is the channel aggrading? Why is the alluvium stratified as it is? The scientist is never satisfied solely with the beauty of the landscape for its own sake. She must question and probe until reaching an understanding of not only why the landscape looks as it does, but how it got that way and how it is likely to change in the future. The scientist is never satisfied solely with the beauty of the landscape for its own sake. She must question and probe until reaching an understanding of not only why the landscape looks as it does, but how it got that way and how it is likely to change in the future. Is the composition harmonious or discordant? What is going on here anyway? Here is an example of the way one might assemble facts to make judgments about a landscape. The big green tree, referenced in Bob Nolan's song Cool Water, is likely to be a cottonwood, the inference being that it stands beside a desert spring where the water issues cool from the earth. The experienced desert traveler might read the landscape and head toward that tree in search of a thirst-quenching drink or a nap in the shade. If that big green tree were old and decadent, more dead than alive, and surrounded by a grove of young juniper trees, the traveler might guess that the water table had dropped and the spring gone dry. One learns to read the landscape more proficiently with practice. With experience, critical observations are made more quickly, but unfortunately one's conclusions are still fallible. Could the tree be just a mirage, the spring but a wish? In reading the landscape, the reader must always be ready to take a second look and ask another question. In this book, Reading the Landscape focuses on stream channel incision and its likely origins. It is practiced not only to identify a problem, but also to determine the probable cause of the problem, unravel its history, and identify alternative solutions. What processes shaped the watershed? What forces altered the stream channel initially? What interactions between the biotic and abiotic processes in the watershed promote greater or lesser stability in the ecosystem? What must be done to stop the gully, reconnect the channel with its floodplain, rejuvenate the meadow, or restore the bosque? Where is the water coming from? Where is it going? Where should it be going? Why? Could it ever go there again? A person skilled in reading the landscape takes in and assesses many complex factors simultaneously, thinking quickly, almost instinctively, only to be interrupted by some disconnect in the facts and a shift in the train of thought. At some point, more information is needed and more facts must be gathered before an understanding of the story of the landscape and its history can continue. In the analogy of the landscape artist, it's as if a random, discordant line were to draw the mind's eye out of the picture, leaving it to wander in search of harmony and focus. So what does the practiced reader of landscapes see when seeking a cure for a damaged creek or dysfunctional watershed? She sees geology, typography, geomorphology, soils, hydrology, aspects of plant and animal ecology, and the effects of disturbances. Her focus is on gaining an understanding of past and present processes at work on the landscape. Her reading is orderly and deliberate, addressing questions of geology, geologic processes, typography, watershed condition, water quality and quantity, vegetation, ecology, natural disturbances, and human influences. Appendix F, Field Worksheet for Reading the Landscape, page 200. Geology. Geology is the scientific study of the structure and origin of the earth and the processes that have formed it over time. In reading the landscape, a basic knowledge of local geology is essential. One handy reference is the appropriate volume from the Roadside Geology series by Halka Chronic, which is available for most Western states. Books in this series identify the dominant rock formations by geological period, prominent surface features, and how these landforms have been modified by events that occurred during the Quaternary period, most recent. Geologic history and major landforming events such as tectonic uplift, volcanism, and glaciations are noted as to when such events occurred. Each formation erodes to produce a unique sediment supply, alluvium, for the local streams to transport. This section discusses 3 examples from particular locations that produce alluviums dominated by different particle sizes. Briefly discussed here in order of increasing dominant particle size are clay bed systems, silt bed systems, and sand bed systems. Lastly discussed is a low sediment supply leaky watershed example. A typical watershed will be a combination of these sediment rock types. For example, clay. The Chinle Formation of the Colorado Plateau consists of interbedded clay stones that weather down into clay-sized particles. The chemical properties of clay dictate its behavior in a stream system. Clay particles chemically bind to each other in the presence of water, forming a substance that, when dry, is harder to erode than silt or sand, the latter having no cohesion whatsoever. Once a gully has started in a clay alluvium, it tends to deepen much faster than it widens. Because the channel bottom is in direct contact with water during a rain or runoff event, it can easily be softened, while the channel sides remain dry and as hard as baked adobe. Silt. The rocks of the Jemez Mountains between Española and Cuba, New Mexico, are volcanic in origin. Rapid decomposition of this volcanic rock produces an abundant supply of fine silt. Silt is highly erodible alluvium because silt grains have very little cohesion and the tiny particles are easily washed away. Ever-deepening rills become gullies and then gorges, seemingly without limit. A classic example is the Rio Puerco, called by Luna Leopold the largest man-made ditch in the world. Photo 6-1, page 122. Sand, gravel, and larger particles, while abundant in the headwaters of most creeks, are virtually absent from broader valleys with little slope. Historic slope wetlands are common, but most are now degraded due to human disturbances and the fragile nature of the deep silt deposits. Sand. The Chusca Mountains on the Navajo Reservation in New Mexico and Arizona are comprised mainly of sandstone, formed during the Mesozoic era that eroded and was subsequently redeposited during the Oligocene epoch. These sandstone formations erode back to sand-sized particles. Gravel and cobble-sized sediments are rare. Bank building is rapid, and alluvium accumulates as deep sandy deposits that are easily eroded again because sand grains do not bind together unless deposited with clay. This total lack of cohesiveness allows sand stream banks to slump and become over-wide. Stream sinuosity is characteristically low, and stream channel width-depth ratios are high. In reading the landscape of this area, one would see this as the normal condition. A channel with cohesive banks and high sinuosity would be unusual for a sand system and a cause for further investigation to learn why. Leaky watershed. The Sandia and Manzanita Mountains east of Albuquerque, New Mexico, are capped by limestone of the Permian period resulting from uplift associated with the Rio Grande Rift. Julian, 2005. The limestone strata in this formation is highly fractured both vertically and horizontally. During storm events, a large proportion of the rainfall trickles down into these fractures instead of becoming surface runoff. Therefore, stream channels in the area are smaller than might be expected for the size of the watershed. Cedro Creek, 2009. Also, because limestone erodes slowly, the annual sediment yield from decomposition of the bedrock is small, and alluvial deposits collect slowly and are shallow. Streams tend to be tightly controlled by faults. Sediments are cemented together by travertine deposits. The result is that streams in this area are difficult to treat using the induced meandering method because little sediment is transported and available stream power is weaker than expected due to diminished flows. In reading the landscape, it is important to pay close attention to deposits laid down during the Pleistocene and Holocene eras of the Quaternary period, the most recent in our geologic history. Some geologists now consider the Earth to have entered the Anthropocene era because human influences have altered many landscape-forming processes over a large portion of the Earth's surface. The Pleistocene era, or the last ice age, was an important time in shaping land surfaces in the Southwest because this was generally a wet time. A few of the higher mountain ranges were shaped by glaciers and exhibit typical glacial terrain features such as moraines, cirques, and tarns. Scattered across lower elevations are lacustrine lake features dating to the Pleistocene when rainfall was much higher than it is now. Lacustrine features can be detected by their flat terrain, fine textured sediments, absence of terraces, and frequently by the presence of relict shores. Lacustrine landforms include Lake Valley near Deming, New Mexico, San Augustine Plains west of Socorro, New Mexico, and Wilcox Playa, Arizona. Spur Lake Basin near Luna, New Mexico, is a Pleistocene lake bed that was severely altered and drained for agricultural use during the early 20th century. Geography. Geography is the study of the physical features on the Earth's surface. Geographers have divided the surface into areas or regions of broadly similar features. Examples include the Great Plains region, the Rocky Mountain region, and the Basin and Range region. In the eastern United States, regions include the Coastal Plain, the Piedmont, the Appalachian Mountains, and the Ohio River Valley. Regions may be divided into smaller geographic provinces, such as the Southern Rockies, the Southern Appalachians, the Cumberland Plateau, and the Mississippi Delta. With each additional subdivision, the defining natural features of the area become more discrete, clearly and uniquely distinguishing the area from its neighbor. Features of interest might include geographic boundaries, latitude and longitude, average elevation and range of elevations, dominant geologic features and processes, typical shape of drainage patterns, precipitation zones, characteristic soils, and dominant plant communities. The Colorado Plateau is a prominent division of the Basin and Range region of the Southwest. This region includes an area of 130,000 square miles in the Four Corners area of New Mexico, Arizona, Colorado, and Utah. The climate is arid, with an average annual rainfall of 12 inches, more or less equally distributed between winter and summer. These drylands are where potential evaporative loss exceeds precipitation. Elevations range between 12,000 feet and as low as 2,000 feet, averaging about 5,500 feet. Dominant vegetation is cold desert shrub, including big sage, black sage, greasewood, and saltbush, with pinyon juniper woodlands and ponderosa pine forests at higher elevations, and various grasslands on mesas and swales. The area is a broad, flat plateau of sedimentary rock formations made up of sandstones, siltstones, limestones, and mudstones. Formations date to the Triassic, Jurassic, and Cretaceous periods. The terrain is deeply dissected by deep canyons such as the Grand Canyon, photo 6-2, and punctuated by volcanic peaks such as Mount Taylor and the San Francisco Peaks. Basalt flows like El Mapai and volcanic cores like Shiprock and Cabazon are also common landscape features. Wetland and riparian areas on the Colorado Plateau consist of widely separated perennial streams and isolated spring-fed oases. Soils are alkaline and highly erodible. They are cut by deep, rapidly advancing networks of gullies throughout, as generated by the effects of widespread overgrazing, poorly drained roads, and extensive mineral extraction. The above brief description of the Colorado Plateau is intended to illustrate how knowledge of the geography of an area can lead to an understanding of the landscape from the standpoint of watershed function and stream stability. Understanding the geography is valuable in that the lessons learned in one part of the region or subregion can be extrapolated to aid in understanding another. From the standpoint of the river restorationist who is focused on the treatment of incised channels, the salient characteristic of the landscape is its fragility, especially during periods of drought and/or heavy grazing pressure. From the standpoint of the river restorationist who is focused on the treatment of incised channels, the salient characteristic of the landscape is its fragility, especially during periods of drought and or heavy grazing pressure. That feature alone must be uppermost in the mind of the reader of the landscape. Topography. Topography is the canvas upon which a landscape is painted. Topography is the study of Earth's surface features. The topography of an area includes such factors as elevation, relief, changes in elevation between points, slope, steepness and extent, position on slope, aspect, north-south orientation, drainage patterns, etc. Topographic features include mountain peaks, ridges and passes, mesas, buttes, hogbacks, terraces, valleys, streams, lakes, wetlands, springs, canyons, and washes. Figure 6-2. Of the many different topographic features affecting watershed function, slope, aspect, and relief are central to reading the landscape. Slope. Slope is the measure of the steepness of the landform. The steeper the slope, the faster water moves across it. Position on slope is important. The further down slope, the more accumulated flow will move past a given point. Soils tend to be shallow at the top of a slope and deepen at the base. Where slopes steepen, water speeds up. Where they flatten, water slows down. Soil erosion rates are high on steep slopes and low on flatter slopes. Soil depths, moisture availability, and plant growth tend to vary accordingly. Slopes may be uniform from top to bottom, but more often they vary in steepness. A slope that is less steep at the bottom would be concave. One that is steeper at the bottom would be convex. The point where the steepness of slope changes is known as a slope break. A long slope in mountainous terrain might have numerous slope breaks interrupted by cliff lines or escarpments. Each would have its own effect on slope, steepness, the velocity of surface water runoff, the accumulation of soil particles, soil depths, and other factors of importance to reading the landscape correctly. Figure 6-3, page 125. Aspect. Aspect refers to orientation or the direction a landform slopes, whether northerly or southerly. In the northern hemisphere, a south slope faces toward the noon sun. South slopes are warmer than north slopes. South slopes dry more quickly than north slopes. Snow accumulations are less because soils are warmer and snow melts more quickly. Site productivity is lower on south slopes and higher on north slopes. Plant species composition, tree heights, and canopy densities vary greatly between northerly and southerly slopes. Soil erosion rates tend to be higher on south slopes. Soil depths tend to be greater on north slopes. Soils on northerly slopes also contain higher proportions of humus or accumulated organic matter, and because of lower soil temperature, their oxidation rates are slower. More water permeates into and is held by soils on northerly sites. East and west slopes are intermediate between those facing north and south, depending on the degree of deviation, but east slopes tend to hold more moisture than west slopes because air temperatures are lower in the morning than in the afternoon, and prevailing winds from the west tend to be more drying. Relief. Relief is a measure of the difference in elevation between 2 points, and in total a measure of the evenness or unevenness of the land surface. The greater the relief between higher and lower elevations, the greater the difference in mean annual temperature. Mean annual temperature decreases by about 3.6 Fahrenheit with each 1,000 feet increase in elevation in the troposphere, the lowest layer of the atmosphere where we live. This is an average value and varies from season to season. The decrease is slightly less in the summer and slightly greater in the winter. Temperature variability is greater in valley bottoms than on ridge tops because cold air accumulates in valleys. Various adjectives are used to describe relief: flat, slight, gently rolling, pronounced, rugged, or extreme. In relatively flat or rolling terrain, slight differences in relief, slope, and aspect can make relatively large differences in soil depth, moisture retention, and erosion rates, which are reflected in the vegetation. Soils. Soils vary enormously in fertility, productivity, permeability, water holding capacity, and erodibility. Other properties include texture, depth, composition, materials, humus content, and temperature. Soil maps and descriptions are generally available from local offices of the USDA's National Resources Conservation Service. Descriptions include information regarding soil capability and limitations for different uses. Soils are said to be alluvial if formed by the action of moving water. Fine-grained alluvial soils are deposited by water flowing over floodplains or lake beds and are found in aquatic communities. Colluvial soil types form under the force of gravity, as when soil particles roll, tumble, or slide downhill. Residual soils develop in place through the gradual decomposition of parent material. Soils are classified according to their relative content of sand, silt, and clay. When all three are present in relatively equal amounts, a soil is said to be a loam. Soils that are saturated for prolonged periods, i.e. seasons, develop under anaerobic, oxygen-free conditions become hydric. Hydric soils can be alkaline, acidic, or saline. Permeability and water-holding capacity varies immensely among different soil types. Sidebar: hydrologic soil groups. Water moves through soil under the force of gravity and by capillary action. While most soils are hydrophilic, they like water, some soils are hydrophobic, they dislike water, and will absorb water depending on the chemical composition and structure. Some hydrophobic soils are natural and some are created by man through poor land management practices. Most desert soils are naturally hydrophobic. Fang, 2000. Changes in soil are reflected in changes in vegetation. When reading the landscape, an apparent change in plant species, composition, height, density, or distribution may indicate a difference in soil type and its ability to capture and hold moisture. Hydrology. Hydrology is the study of the movement of water through the hydrologic cycle, figure 6-5. Every high school student learns that the hydrologic cycle begins with evaporation of water from the sea. Water is transported as water vapor by the atmosphere, precipitated from the atmosphere as rain or snow, or in some cases as condensation from fog. It runs off upland surfaces and is discharged into streams and eventually returns to the ocean to complete the cycle. Along the way, some of the precipitation may be intercepted by vegetation. This moisture is evaporated directly into the atmosphere. Some may be utilized by vegetation and returned to the atmosphere by transpiration. Some may infiltrate the ground surface and percolate downward through the soil to recharge groundwater aquifers, and some may flow laterally through the soil to recharge a stream. Some water may be captured forever by a closed basin, and some, originating as snowfall, may return directly to the atmosphere by sublimation from the solid state ice to the gaseous state water vapor, without ever melting into water. When one New Mexico rancher was asked, "What happens to the snow in this part of the Great Plains?" he replied, "Oh, it just blows around until it wears out." Sublimation in action. In reading the landscape, it is important to gain an understanding of the local hydrology in order to understand its influence on channel morphology. One needs answers to such questions as, when does precipitation normally arrive, and how is it distributed seasonally throughout the year? What is the normal amount of precipitation per event season or year? What is the normal storm duration and intensity? And how great are the likely variations? How quickly will water run off? How much discharge is likely to result from a precipitation event of a given magnitude per unit area of land? How fast will the stream rise and fall back to pre-storm levels? Soil horizons. O horizon is comprised of organic materials that generally form above the mineral soil and are derived from dead plant and animal residues. Generally absent in grassland regions. O horizons usually occur in forested areas and are commonly referred to as the forest floor. A horizon consists of the most intensely weathered rock material and contains the enough partially decomposed organic matter to give the soil a color darker than that of the lower horizons. Precipitation infiltrates down through the A horizon. In so doing, the water may dissolve soluble minerals and carry them down. This process is known as leaching. E horizon. These are zones of maximum leaching or eluviation of clay, iron, and aluminum oxides, which leaves a concentration of resistant minerals. An E horizon is usually found underneath the A horizon and is generally lighter in color than either the A above or horizons below. This horizon rarely occurs in soils developed under grassland. B horizon, zone of accumulation or zone of deposition. In drier climates, many of the minerals leached from the A horizon accumulate in the B horizon. This zone is somewhat protected from surface processes. In arid and semi-arid regions, calcium carbonate or calcium sulfate may accumulate in the B horizon, forming caliche. C horizon consists principally of very coarsely broken up bedrock and little else. Montgomery, 1997. Brady, 1999. Infiltration. In reading the landscape, the most important observation to make about soil is its permeability and water-holding capacity, as well as its composition, structure, and depth. The next most important observation relates to the hydrologic condition of the soil surface.
Infiltration rate is directly related to the amount of vegetative soil surface cover. The more vegetative cover, the better the infiltration, and therefore the less runoff. When the rate of precipitation exceeds the rate of infiltration, surface ponding results. Water may be contained within small irregularities or indentations in the soil surface layer, but when these fill, water begins to flow as runoff, draining across the landscape and collecting in stream channels. In reading the landscape, an observer would look for indicators of rapid infiltration or indicators of natural conditions or land uses that might lower infiltration rates and cause precipitation to run off more quickly than expected. Infiltration does not occur on frozen, icy soils, so runoff occurs rapidly from rain that falls on frozen soil. Water infiltrates rapidly into sandy soils, less rapidly into loamy soils, very slowly into clay soils, and hardly at all into rock or other impermeable layers. Some soils may have a high infiltration rate at the surface, but a low infiltration rate in deeper layers. For other soils, the reverse may be true. Soil with a well-developed A horizon or a thick layer of organic material on its surface, such as leaf fall or crop residue, would be expected to have a high rate of infiltration and produce less runoff than one where the vegetation had been removed by fire or overgrazing. Soil with a high density of macropores will absorb precipitation rapidly. Compacted soil absorbs water slowly, therefore yielding more runoff per unit area and retaining less. Forest soils with deep organic layers and abundant macropores may produce little or no runoff during summer rains, but abundant runoff during snowmelt if soils are frozen. In reading the landscape, it is important to make an assessment of apparent infiltration rates and the likely water-holding capacity of the soil. Soil profiles can be readily observed along road cuts, ditch banks, and erosion gullies. Sidebar: Soil horizons. Peaks of flow. Stream discharge can be expressed in many ways. Cubic feet per second or per square mile, cubic meters per second or per hectare, and average daily discharge or maximum or minimum discharge. The seasonal and daily variations in discharge rates are an important aspect of hydrology. During winter, stream flow normally peaks in late afternoon and early evening after a warm sunny day, and is minimal at mid-morning after a hard night's freeze. In contrast, during the warmer growing season, daily in-stream peak flows occur during nighttime hours when evapotranspiration ceases. Minimum flow occurs in late afternoon due to transpiration by riparian vegetation. Ecology. Ecology is further divided into autecology and synecology. Autecology studies the ecological needs of the individual, and synecology addresses how individuals relate to each other and to their environments. Reading the landscape uses both sciences to identify and interpret condition and trend. An important concept of ecology is that some species are adapted to a broad range of conditions under which they survive, prosper, and reproduce, while others have very narrow ranges of adaptation. Those having narrow tolerances can be used as indicators of soil site characteristics or other parameters. For example, Apache plume is a small to medium-sized shrub that occupies coarse, textured sand and gravel bars along the periodically wettened margins of ephemeral stream channels, but is seldom found along the edges of perennial channels. If a patchy plume is found along a stream bank, one can assume with high confidence that the channel is indeed ephemeral, an important clue to reading the landscape. Many woody species that occur along the margins of ephemeral creeks soon die if the water table rises. Thinleaf alder, a tall woody shrub, is adapted to the margins of fast-moving perennial streams with gravel banks and well-aerated soil and water. Thinleaf alder does not occur along ephemeral streams or streams bounded by clay banks with poor aeration. Alders are easily drowned behind newly created beaver ponds when dissolved oxygen levels decline. Some riparian species can survive relatively long periods of inundation during the dormant season, but only short periods during the growing season. By knowing these relationships, one can interpret the history of a site and interpret ongoing processes. By contrast, if an upland species, such as the one-seed juniper, is observed growing on a stream terrace in the shade of old-growth cottonwoods, one might see this as an indicator of soil desiccation and deduce that the water table had dropped. A second ecological concept important to reading the landscape is that of plant succession, how species of plants compete for space over time. Assemblages of plant species will change over time from early seral to late seral stages as some species outcompete others for sunlight and soil moisture. Following a stand replacement fire at mid-elevations in the southern Rocky Mountains, mixed conifer forests will be replaced by quaking aspen, which sprouts from roots and takes up nutrients released by the fire as they grow rapidly in full sunlight. The aspen may grow in association with other trees, shrubs, and herbaceous plant species such as raspberry and elderberry. Gradually, other woody species which can tolerate more shade and whose seeds are dispersed by the wind begin to take hold under the aspen canopy. Depending on aspect, elevation, available soil moisture, distance from seed source, and other factors, these species may include ponderosa pine, Douglas fir, white fir, Engelmann spruce, or limber pine. Eventually, the shade-tolerant species overtake and replace the shade-intolerant species, and then dominate the site for decades as aspens decline and die. Only another severe disturbance like fire, logging, blowdown, or insect outbreak will cause aspen to once again dominate the site and trigger the process of plant succession. In reading the landscape, a comprehensive knowledge of ecological requirements of species typical of early and late seral stages is essential to tracing the history of a site as evidenced by its vegetation. In reading the landscape, a comprehensive knowledge of ecological requirements of species typical of early and late seral stages is essential to tracing the history of a site as evidenced by its vegetation. A third concept addresses the ability of vegetation to affect the environment itself through the ecological processes that modify the geomorphology and hydrology of the site. For example, point bar evolution begins with a fragile accumulation of sand and gravel and ends with a mature meander apex decades later. Each newly colonizing plant species alters flow characteristics and changes the rate of sediment accumulation, slowly rendering the site unfit for pioneering species and more suitable for latecomers. Those plants that come first are called facilitator species because they make it possible for others to survive there. At mid-elevations, along a moderately steep perennial stream with a Rosgen B channel type in south-central New Mexico or Arizona, as bank building progresses, plant species succession and site modifications might go from spikerush or deergrass to coyote willow, or Gooding willow to cottonwood to velvet ash and sycamore, and finally to Arizona walnut.
Initial plant succession would gradually increase the roughness of the surface, causing more and more sediments to be deposited and making the land surface higher and drier with successive flood events. Another example is the case of dehydration and re-wetting of a former wet meadow where plant succession, following a disturbance that lowered the water table, might proceed from a stand of sedges and rushes to upland species such as rubber rabbit brush, ponderosa pine, and blue grama grass. If the conditions that drained the site, such as a misplaced road culvert, were corrected and the site rehydrated, a change in soil moisture conditions might be reflected first in the decadence and mortality of the rabbit brush, then the yellowing, decreased vigor, and ultimate death of the pines, and finally, the replacement of the grama grasses by Baltic rush, western wheatgrass, beaked sedge, redtop, agrostis, and other wetland species. Woody plants would disappear from the site as soils gradually become anaerobic. An ability to recognize steps in the sequence would help the observer to read the landscape, date events that triggered change, and determine the history of the site. The next concept relates to the occupancy and use of successional vegetative stages by their faunal counterparts. In the case of the restored wet meadow, occurrence and use by adapted bird species and highly mobile large mammalian species would likely change before a response from small mammals, reptiles, and amphibians became evident. Slate-colored juncos and common flickers might be replaced by brewer's blackbird and house wrens. Use by elk might increase as the growth of protein-rich sedges increases. If the site contained pools of open water, mallards, common snipe, and solitary sandpipers might return. As the diversity, density, and height of the sedge community increased, voles might recolonize the site and pocket gophers might become more numerous. The effect of these small mammals would be to increase the pattern density and depth of soil macropores, tunnels, that would allow runoff from melting snow to infiltrate the soil more rapidly and more uniformly. The increasing numbers of voles and pocket gophers would support an increased diversity of raptors, hawks, and owls, as well as gray fox, long-tailed weasel, coyote, and other carnivores. Familiarity with the habitat requirements and feeding behavior of local wildlife species could help the observer to determine the successional stage of the recovering wetland site while postulating on the history of events that caused its initial devastation and eventual recovery. Vegetation of ephemeral channels. Richard Dick Petty in New Mexico Vegetation, Past, Present, and Future, describes 7 riparian plant communities typical of ephemeral stream systems. The species are considered semi-riparian rather than riparian obligate, indicating that stream side soils are not hydric. Dick Petty's 7 communities or series are dominated by different species depending upon elevation and climate of the area. From the higher elevation, about 7,000 feet, to the lower elevation, less than 4,000 feet. The dominant species in order are greasewood, salt bush, rabbit brush, Apache plume, burrow brush, brickle brush, and honey mesquite. Photo 6-3. Therefore, upon observing a floodplain dominated by one of these species, one could safely assume that the water regime was ephemeral. That assumption might be confirmed by having some knowledge of the geography and climate of that area. For example, ephemeral tributaries to the Rio Puerco in the vicinity of Cuba, New Mexico at 7,000 feet elevation are in fact dominated by greasewood. 40 miles further to the west, the banks of Daniel Wash at the same elevation, but in a slightly drier climate, are dominated by four-wing saltbush.
Dense monotypic stands of saltbush have stabilized the banks of Daniel Wash and function much like shrub willows in protecting the banks of this ephemeral channel from erosion during flood events. In southwest New Mexico, at 5,000 and 6,000 feet elevation, deergrass often dominates arroyo banks and rabbit brush is common on the terraces. Photo 6-4. In southern New Mexico, at much lower elevations and in a more arid climate, honey mesquite might perform a similar function. Vegetation of perennial and intermittent channels. Robert C. Zarrow, in Riparian Forest and Scrubland Community Types of Arizona and New Mexico, describes 28 riparian forest and riparian scrub community types typical of moist soils fronting perennial and intermittent stream channels. Figure 6-6. As with Dick Petty's classification system, the plant communities differ primarily by elevation and climate, although Zarrow addresses the relative importance of several additional factors, including stream-bearing aspect, stream gradient, and valley cross-sectional area. From high elevation to low, the dominant riparian community types range from the big-tooth maple, white fir, blue spruce, and narrowleaf cottonwood types above 7,000 feet to Gooding willow and velvet mesquite types below 3,300 feet. Zarrow, 1989. Stream gradient was the second most important factor in determining the distribution of the Arizona sycamore type and the Arizona walnut, Arizona sycamore community types. With some knowledge of riparian community types, the observer might infer that the stream was not only perennial, but also at mid-elevation and relatively steep, probably greater than 2% slope. At Santa Clara Creek in northern New Mexico, Zeedyk classified 17 stream reaches not only according to the Roskin channel type, but also to the dominant vegetation type, coining the term bioreach. For example, the highest reach, 8,500 feet, was a Roskin E channel type dominated by blue spruce. Roskin E blue spruce, a mid-elevation reach, was Roskin B type dominated by narrowleaf cottonwood, and the lowest reach with the flattest gradient adjacent to the Rio Grande was a Roskin C type dominated by Fremont cottonwood. While not a flawless approach to classification, with local experience one could make a reasonable assumption at the Roskin channel type simply by noticing the adjacent plant community, especially if both overstory and understory species are considered. Human influence leading to channel incision. A complete listing of human influences on streams and watersheds leading to channel incision is beyond the scope of this book. Major causes of incision are grouped and listed by categories. Channel incision is not only the result of a single impact, but more often the result of multiple cumulative impacts having synergistic effects. Deliberate mechanized manipulation of channel dimensions, plan form, location, or alignment resulting in a deeper, narrower channel includes channelization, straightening, deepening, snagging, removing trees and woody debris from stream banks, channels, and flood-prone areas, realignment and relocation. Examples include flood control protection and channel realignments at road stream crossings, culverts, bridges, etc. Deliberate channelization of dispersed surface flows in order to contain surface runoff within a single well-defined channel. Concentration and acceleration of flows accelerates bed scour downstream and head cutting upstream. Examples include wetland or railroad drainage for agriculture, mosquito control, drainage of alluvial fans to promote urban expansion, road drainage ditches and dikes used to intercept, collect, and contain upslope runoff to direct it through a single culvert. Floodplain encroachment confines stream flows to the bankful channel, causing accelerated stream velocities that lead to bed scour and erosion of the opposite bank. Examples include
road or railroad construction parallel to a channel, road embankments perpendicular to a channel, backfilling on floodplain to create lands for real estate development, and mine tailings stored on a floodplain. Wide-scale removal or alteration of vegetative cover can cause watershed degradation by exposing soils to compaction and accelerated rates of soil erosion and runoff. Increasing discharge and flood velocity causes channels to downcut or widen. Increased sediment supply may initiate channel evolution to a different channel type. Examples include wildfire, overgrazing, and off-road vehicle traffic. Urbanization can degrade the watershed by the replacement of native soils with impermeable or less permeable surfaces, pavement. This increases stormwater discharge and peak flows. Roads, trails, and sidewalks, parking areas, housing developments, and commercial real estate developments are all new impermeable surfaces. Loss of riparian or wetland vegetation can destabilize a stream bank. Examples include bank trampling or collapse, livestock or wildlife herbivory on stream bank vegetation, stream bank trampling by human foot traffic, off-road vehicle traffic, clean farming practices, and burning. Loss of predators, such as wolves, change behavior patterns and populations of prey, such as deer and elk, resulting in increased herbivory of stream-side vegetation. Inadvertent stream capture by old or abandoned roads, trails, and irrigation ditches. Examples include abandoned wagon roads, livestock trails, off-road vehicle trails, and abandoned acequias. Diminished sediment supply, loss of channel-maintaining flows due to artificial dams and impoundments. Examples include dams and impoundments for irrigation diversion or flood control, farm ponds, livestock tanks, erosion-controlled dams and ditches, groundwater pumping, and check dams and gully plugs. Reading the landscape case studies. The following 3 case studies illustrate the process of reading the landscape through careful observation of the site. They describe sites where restorative treatments were applied after carefully considering the geology, geography, topography, soils, hydrology, and ecology of the area, and the human influences affecting the natural drainage pattern. They describe sites where restorative treatments were applied after carefully considering the geology, geography, topography, soils, hydrology, and ecology of the area, and the human influences affecting the natural drainage pattern. Hallman Wet Meadow. A slope wetland is a perennially wetted alluvial fan. Slope wetlands are common in higher elevations of northern New Mexico. This landform is sub-irrigated at base flow by an underlying gravel layer and is subject to inundation by overbank floods. Hallman Wet Meadow is a high elevation 9,500 foot slope wetland on Carson National Forest in northern New Mexico, approximately 60 acres in size with a watershed of 1,386 acres. As is often the case, the wetland soils at the site are shallow to bedrock, in this case only 2.5 feet deep. A 2-stage headcut was advancing up valley at the rate of 6 inches per year, draining the site upstream from the headcut. The meadow was populated by wetland obligate and wetland facultative species such as Carex mycoptera, meadow sedge, and Iris missouriensis, Rocky Mountain iris. Downstream, the drier wetland surface had terraces separated by an ephemeral gully approximately 2 feet deep and 8 feet wide. Question: what had caused the headcut? Answer:
By searching downstream for the present location of the head cut, a spot was located where an old barbed wire fence had crossed the meadow at a right angle to the direction of the slope. The wire had been removed and the posts pulled from the ground to lay where they fell. A deep depression in the soil paralleling the old fence line on the north side revealed the presence of a former cattle trail that crossed the meadow at an angle just upstream of the fence. The cattle trail had become rutted and captured hill slope runoff. Water intercepted and collected by the trail was directed to the gully bottom at the point of crossing. The trail had concentrated and accelerated the flow, resulting in channel incision. Erosion moved up valley from the point of the trail crossing. It was postulated that the cattle trailing along the fence had broken through the wetland sod, exposing the fragile wetland soils to accelerated erosion and initiating head-cutting action. The rate of erosion was accelerated by surface flows captured and diverted by the cattle trail. During the interim period, the head cut had moved upstream to its present location about 40 feet in 60 years, or 8 inches per year. Treatment. A log and fabric step pool structure was installed to arrest the head cut. Photos 6-5, 6-6. And a bypass channel constructed to route surface flow around the head cut to resaturate the terrace. Sidebar. Worm ditch. Page 135. Figure 6-6. Photos 6-7. 6-8. Ironically, the old fence posts that had created the problem were collected and used as the logs for this treatment. Post Office Flat. Post Office Flat on Redondo Creek is a high-elevation, 8,000-foot wet meadow in the Zuni Mountains, Cibola National Forest in west-central New Mexico. The meadow is about 15 acres in size with a watershed of 3 square miles. The watershed is forested predominantly by ponderosa pine with Douglas fir, white fir, and aspen on the more mesic northerly slopes. The meadow had been the site of a small community boasting a post office during the 1920s when the forest was first logged while still in private ownership. The land was subsequently acquired by the U.S. Forest Service during the 1940s. Concentrated grazing over a period of at least 60 years had converted the native sedge community to a stand of Kentucky bluegrass, dandelions, and grandma grass. A series of low, discontinuous head cuts were connected by shallow gullies, and the water table had dropped about 3 feet. The meadow sloped at a grade of 1%. Redondo Creek was an intermittent channel both upstream and downstream from the meadow. Question. What caused the head cuts and lowered the water table? Answer. The meadow, photo 6-9, page 137, had been impacted for many years by 2 low-standard roads that intersected at the downstream edge of the meadow. One road, not visible in the photo, closely paralleled the east meadow edge on Valley Right and had captured Redondo Creek for about 200 feet, causing it to enter the meadow downstream from its natural point of entry and, therefore, drying the upper end of the meadow. The second road crossed Redondo Creek at the lower end of the meadow with an unimproved ford. Over many years, traffic use and spring floods had lowered the base level of the creek by about 3 feet. The resulting head cut had eroded upstream for about 120 feet, starting a gully and draining the meadow. Soil compaction from continuous, season-long grazing had exacerbated the problem. Treatment. First, the upstream road-caused gully was plugged.
diverting the stream to the meadow surface at its natural point of entry, rehydrating the relict hydric soils. Then, the incised road crossing, unimproved ford, was replaced by a road embankment and culverts having their invert elevation equal to the historic meadow surface, top of the gully bank. This treatment restored the sponge effect of the meadow. Photo 6-9. Water stored in the alluvium was once again released year-round as increased base flow in the downstream channel. Finally, the livestock grazing method was changed from season-long use to short-duration use that enabled recovery of the plant community. Loco Creek. Loco Creek, located south of Quemado, New Mexico, drains a small watershed of 670 acres and flows through both public and private lands for 3 miles from its headwaters in the Gallo Mountains into Largo Creek. One can begin to appreciate how loco this creek is by looking at the top of the high arroyo cutbanks in photo 6-10 and noticing several things. The land above the bank slopes uniformly to the left, and the bank on the left is slightly lower than the bank on the right. There is a certain place one can stand where the gully is not visible, and the original valley bottom is apparent several hundred feet to the right of the gully. The present location of the creek is not in the historic valley bottom, but in a 15-foot deep gully that is located on the side of a gentle hill slope. Question: what caused the gully to form, and why is it situated in its present location? Answer: such seemingly geomorphic anomalies are actually quite common and have a simple cause: stream capture by a road. In the case of Loco Creek, historic records, recollections of the old rancher, and a careful reading of the landscape tell the story. As the old wagon road went down the valley, it crossed the stream at an angle. Farther down valley, the road went around a very low ridge. Over time, the road became more and more deeply rutted into the landscape. This happened because local hill slope runoff was captured in the wheel ruts, causing the road to cut deeper and deeper with every runoff event, while remaining quite passable during the dry season. Eventually, the ruts carried all runoff from the point where the road crossed the stream. At this point, whenever there was a runoff event, the road began to operate like a diversion channel, and some of the water from the stream flowed down the road. At that time, the problem could still have been easily fixed with a shovel, but there was no fluvial geomorphologist to point out what was about to happen. The next several flood events must have completed the job of stream capture by the road, which was now narrower, deeper, and straighter than the natural stream channel had been. The entire stream flow was therefore going down the road faster than when the stream was in its natural channel, increasing erosive power and transport capacity. This initiated an erosional feature called a head cut, in which concentrated flow scoured the channel in one place, creating a drop-off with an undercut. Head cuts travel upstream, lowering the bed of the channel in the process. In the case of Loco Creek, where the valley fill is composed of sand and silt, the head cut migrated toward the headwaters at a startling rate. Over many years, the head cut started by a little wagon trail progressed several miles up the stream channel, ultimately creating a deep canyon. The canyon goes under a fence that was built in 1935. That fence is still standing, but the hand-dug juniper fence posts are dangling from the rusty old barbed wire 15 feet in the air. Those narrow, steel-rimmed wagon wheels were notorious for creating ruts. The stream captured by old wagon roads degraded many streams that are still in the process of recovery. Unfortunately, stream capture by low-standard 2-track roads and ATV trails is all too common today. Treatment. In this case, the treatment of induced meandering was implemented over a 2-year period along 1 mile of the lower reach that intersects Largo Creek. Picket baffles, post vanes, and wicker weirs made from local materials were used. There was a plentiful supply of sediment, but a 3-year period of drought followed by 2 major storm events pushed the limits of the treatment for this gully. Some structures performed well, building point bars and stabilizing the grade, while others were damaged or completely destroyed and had to be repaired. The preventative solution to gullies caused by low standard road capture is always to cross a stream at a right angle to the flow. The preventative solution to gullies caused by low standard road capture is always to cross a stream at a right angle to the flow. The perpendicular crossing must start above the flood-prone area, dip down to cross the stream, and proceed back up the other side above the flood-prone area before making any turns. The solution could also include a floodplain culvert with inlet placed at correct elevation, Chapter 5. Culverts are generally not advised for low-standard dirt roads crossing ephemeral watercourses, however. Field worksheet for reading the landscape. From the perspective of this book, reading the landscape is done to determine the causes of observed channel incisions, to ascertain the likelihood that continued erosion will lead to deeper channel incision, and to draw a mental picture of how the natural or stable landscape might look. Such an understanding is gained by asking the right questions. The field worksheet, Appendix F, page 200, seeks to lead the observer through the process of reading and understanding a landscape by asking the right questions in the right order. The questions help to focus the eye of the artist on the scene as the picture is composed and the details finally colored in. The questions progress from the very general to the very specific, and are intended to foster not only a better understanding of the landscape under scrutiny, but also to create a framework for future reference. Such a framework is helpful in gaining a better understanding of other landscapes. In the worksheet, the questions are meant to stimulate the imagination and lead to other, more incisive questions. Any questions can be skipped, and many can have more than one answer. It may not be possible to answer all of them, but an honest effort will help the careful observer to gain a better understanding of the landscape. Sizing up the landform. This section addresses the broad questions regarding the landscape setting, geography, geology, typography, geologic process, and landform. What is the geographic region or province? What are the geology and morphology of the area in general? What are the characteristic typographic features of the landform? An experienced reader of landscapes might have knowledge of other similar landforms to better understand the one at hand. Sizing up the landform will provide essential background information for evaluating the watershed. Sizing up the watershed. This section leads one to an understanding of the hydrology, soils, and climate of the watershed and its performance by examining such features as size, expected precipitation, precipitation patterns, soils, hydrologic conditions, hydrologic regime, expected discharge, and water quality. An understanding of the watershed will lead to a better understanding of the stream draining it. Sizing up the stream or water body. This section provides the information needed to characterize the stream or water body and predict its behavior. The characterization might lead to a determination that the stream was typical or atypical of other streams in the area and provide some indication of potential problems worthy of further study. For example, the answer to, is the hydro period sufficient to sustain wetland vegetation, would be key to answering the question in sizing up the vegetation. Do species present indicate maintenance of riparian wetland soil moisture condition? The answer to the question, is the stream discharge depleted or affected by agricultural, municipal, or industrial diversion, would lead to further investigations under anthropogenic influences. Sizing up the vegetation. The dominant vegetation and its pattern of distribution on the landscape will be determined by the factors considered above. By carefully considering species composition, age class distribution, and vigor, the observer will begin to understand the history of the site and have the knowledge to look for specific signs of natural disturbance or human influences on the landscape. Natural disturbances. Signs of various natural disturbances that have altered the landscape might be very obvious or quite difficult to detect and interpret. The impacts of a recent fire or beaver activity could be quite obvious, but the impact of elk browsing on a willow thicket or stream bank gouging by ice flows might be difficult to identify and even more difficult to interpret. Anthropogenic influences. Human-caused influences are potentially too numerous, varied, and intensive to list. However, investing the effort needed to identify, assess, and interpret their effects is essential to understanding watershed and stream channel functions and determining the causes and likely future direction of geomorphological processes affecting the stream channel and its environment. Without an understanding of human influences affecting the site, it is difficult to plan and carry out a meaningful restoration project. Socio-economic and political realities. Even if reading the landscape has been completely accurate, comprehensive, and informative, and even if all physical and biological information needed for developing a restoration plan has been gathered, an understanding of socio-economic and political realities affecting any future projects will still be needed. The project is doomed to fail unless these realities are addressed. Summary. Reading the landscape trains the eye to see and the mind to integrate information gleaned from many sources. Reading the landscape is a never-ending practice for the practiced eye. It is a recurrent, interdisciplinary exercise for anyone trained in the natural sciences. But reading the landscape is not just for scientists. Any careful observer with an inquisitive mind can learn to notice apparent patterns of color, texture, and form positioned across a landscape and subtle differences that just do not fit the scene. What in this landscape seems normal, and what seems out of place? What is the landscape revealing about its origin, its history, its character and condition? What sort of river belongs in this valley? What seems right, a wetland or a gully? A terrace or a floodplain? A forest or a grassland? Pine trees or sedges? Willows or chamisa? Fish or fowl? The answers are there. A brief discussion of basic concepts is provided in the text. Worksheets are provided in Appendix F that lead the observer through a deliberate and orderly reading of the landscape, beginning with its geology, geography, topography, hydrology, and soils, and ending with its vegetation, ecology, and human influences. What seems to be functioning properly? What is not, and why? As rainwater harvesting expert and author Brad Lancaster once remarked while driving across the Valle Vidal, the problem with learning to read the landscape is that I can no longer look at it passively.